gases, and specifically ideal gases. So ideal gases. I'm going to make the quick assumption that we've talked enough uh, informally and that through your past experience, you understand generally or basically what a gas is. And just in case you don't, the properties of a gas are that it has no definite volume, no definite shape. It will expand to fill whatever container it's put into, and it consists of particles, you know, traveling around. Okay? So let's talk about this ideal gas. Now, in nature, many gases behave pretty close to ideal gases, but this is, like I say, an ideal gas. Okay, so at very low temperatures or under certain conditions, gases may not behave like ideal gases. Okay, so we're going to talk about specifically the properties of ideal gases. Okay, so the first thing that we should talk about is the concept of what is actually going on inside a gas. So a gas consists of molecules or atoms, as the case may be, with enough kinetic energy that they don't I guess really exert any forces on one another, except when they collide. Okay? And speaking of those collisions, in an ideal gas, they are perfectly elastic. So collisions between particles of a gas are elastic. Okay? And what that means is that the kinetic energy is conserved during those collisions. How do we know that that has to be true? Can anyone tell me why this has to be true when thinking about a gas? What would happen if it weren't true? What if kinetic energy was not conserved during collisions inside of a gas? What would start to be lost? Ah, good. Right. So just do a little recall here. Just remember, if we have some kind of container here, we'll make it like a can, with gas in it, and you put a thermometer inside here. Okay. The thermometer is interacting with the gas particles, and the particles in the thermometer are receiving some of the energy from these gas particles that are bouncing off of it. Okay, and eventually it comes to the same temperature as the gas. If the collisions between the particles were inelastic, then the amount of energy that comes out of a collision would not be the same as what came in, and over time these would slow down. So gases would naturally cool if that were not true. Okay, so if there was not a conservation of EK in the collisions within the gases would cool. Okay, does that make sense? Cool within a sealed container, right? Not cool as they, like evaporate off your skin. That's a different story. But just any container of gas would naturally cool. So, I guess by deductive reasoning, they must have this conservation. Okay. Let's talk a little bit about pressure. So what is pressure? Well, pressure is the result of a massive number of particle collisions with the walls of the container. Okay, so let's think about, say, like a balloon, for instance, right? So if we take a balloon, and we imagine that we've blown air into the balloon. Okay, what does it feel like if if I touch the outside of a fairly um, well inflated balloon? What does it feel like? Hard, right? You can detect that there's some pressure there. And if you were to say like allow some of that gas out, you'd feel that the balloon would feel softer, it would shrink. Can you tell me what's sort of going on when we think about a balloon? What forces are at play? Yeah. So what forces are at play here? As quick as you can. Okay, okay, we don't need to quite go there. Yeah. No, 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 not quite to that level, right? Uh-huh. Okay. Okay. Good. Okay. So, if this represents the surface of Earth, okay, we know that around Earth there is a layer of atmosphere, and that layer of atmosphere is made up of gas. Okay. Um, it's mainly nitrogen, with a large proportion being oxygen. About 20, I think, 1% is oxygen, and about 78% or so is nitrogen. And this gas is held towards the Earth by the force of gravity. Okay, and the gas is thicker near the bottom, and you can almost, think of it almost like a pile of gas up above you. Um, if you imagine that a gas is kind of like water in a way, like a really thin liquid, then you've probably experienced diving down to the bottom of a pool, and the deeper you get, the more, essentially pressure there is pushing down on you because the column of water above you exerts an overall weight down towards the bottom of the pool and in all directions, right? And we'll talk about all directions in just a second. Well, the atmosphere essentially does the same thing. So if I look at this balloon, okay, there's atmospheric pressure by virtue of the fact that this balloon is down near the surface of Earth, inside the atmosphere, and there are particles from the atmosphere bouncing and smoking and hitting into the outside of the balloon. Okay, and then there's essentially, I guess, an equilibrium between the inward pressure of the atmosphere and the outward pressure from inside the balloon, and they balance out. And the pressure itself is the sum of all of these collective, hittings of particles into the walls, right? So in other words, it's sort of a statistical effect, really. Like all of these particles do not have the same kinetic energy. It's a distribution from low to high, um, and just because, I guess, by virtue of the fact that there's so many of them, um, all of these sort of random kinetic energies end up behaving in a pretty predictable manner. Um, it's sort of like just the general laws of statistics that we sort of run into every day. The more of a group you sample, the closer to an agreed upon mean that you will get, right? Like for instance, if I took the marks, the physics marks of two students, I might get one that gets 98 and one that gets 95 by random chance, right? Then if I just went with that, I might say that students get on average a mark of 96%. That's probably not very realistic. I would have to take a much larger sample, and then I would sort of guarantee myself that I'm going to get a whole slice of the pie, and I will get those students in there who have 40s and 50s or even possibly less. Okay, particles behave in a very similar way, right? There's a spread of particles with very low velocities and very high velocities, but for the most part, right, they follow it's not quite a normal distribution, but kind of like a normal distribution, and therefore you get an average kinetic energy, and therefore you get an average pressure as these particles smash into the wall, millions and billions of times per second. Yeah, question. Yeah. Why do you think a balloon would get less, why do you think the inflation level of a balloon would change with time? What do you think is happening? Yeah, That's probably exactly what's going on. These particles are either working their way like out through the thin rubber, or they're finding their way out through the nozzle of the balloon. Um, there's certain types of balloon that take a very long time to deflate, um, like those silvery mylar ones. When they're properly with that, when they're filled with air, right? They stay inflated really hard for a long period of time. I'm sure you've probably noticed that a helium balloon deflates much faster than a normal air balloon. Okay, why do you think that might be? What's right? That's exactly what it is. The helium, the actual molecules of the helium are smaller and thereby able to work their way out through either through the skin or through the point where it's tied up. I heard an interesting story about Nike Airs, and I don't know if it's true or not, but I don't know if they make them this way anymore. But when I was younger, they made them and they actually had like a air cell in them, like a pouch of air. Yeah, well, it was just like a bladder essentially. And I heard that they originally tried to fill them with air or possibly helium, anyway, some gas, but they were deflating over time um, because the gas was able to work its way out through the rubber that was, meant to contain it. So Nike actually had to start filling with a gas made of a much larger molecule, maybe nitrogen, I don't know. Yeah, possibly. I'm not sure. I'm not convinced it was that though, but maybe it was. And so the interesting fact is that the gas within the Nike Airs is actually heavier than atmospheric air. So by putting them in, filling these cells, you're better off just leaving it, empty, I guess, if lightness is your goal anyway. But anyway, so that's I don't know if that's a folk tale or if that's true, but I like to think that it's true. It seems legit, but I don't know. So anyway, whatever. A lot of science goes into shoes anyways. Okay, so there's kind of what's going on, right? You have this interplay between these two things. Now, what do you think would happen to a balloon if you started to somehow lower the pressure the outer pressure around it? Like say you took it up in like you took it up into the atmosphere where the atmospheric pressure gets lower. What do you think would happen to the balloon? It would expand in size, absolutely, right? Because the internal um, outward pressure can't be contained by the rubber itself, right? And there is some stretch to the rubber, so the rubber is supplying a bit of an elastic force. But as you take it higher into lower and lower pressure, you would notice an expansion of the balloon as the atmospheric pressure is not able to push back in on it quite as well. The opposite is true too. If you take it down underwater, you'll notice that it shrinks. If you ever have the chance to trek up a mountainside or something like that, take a balloon with you and see what happens. It'll be quite interesting. So Shoesmith's all about these sorts of experiments, like with his scuba diving and so on. But I mean, you can even just dive down to the bottom of a pool with a balloon, and you will notice that it shrinks. The pressure of the water crushes it down. Can be done. Okay. Anyways, so there's that. That's kind of what we think about when we talk about pressure. Um, what else do we need to say here? Okay. Let's talk about what units we measure pressure in. Um, so the SI unit for pressure is the Pascal. Okay, and how that's measured is if you imagine a square meter. Okay, and you say have particles from the atmosphere hitting into that, right? They're going to exert some force on there. And when that force equals a total of 1 Newton, you have 1 Pascal of pressure. Okay? So what units you would have is you would have 1 Newton per square meter. Okay? So 1 Newton of force per square meter. This is the Pascal. Um, Standard atmospheric pressure is what? Um, yeah, they used to be 101.5, but now it's just 100. kilopascals. Okay, so it's actually kilopascals, so 100,000 pascals, um, which seems like quite a bit, right? Is it like 100,000 newtons per square meter is pushing down on us at all times, right? What is that in terms of, like if we were to say, consider that in terms of, its equivalent in kilograms, if this were a weight, what would that roughly be, do you think? What would I divide by? About 10, right? So what's 100,000 divided by 10? Right, right. So, something like the same amount of downward force that 10,000 kilograms sitting on a 1 meter squared surface would experience in a vacuum, of course, right? Without that extra atmospheric pressure. So the question is, here we all are walking around under this, seemingly intense pressure, and yet we're perfectly able to exist. Why is that, do you think? Why is that not a problem? There it is, okay? Just like with the balloon, okay, we have our air cavities, so our inner ears, our lungs, our nasal passages, and so on, all contain air at the same pressure, and it exerts an outward force equal to whatever inward force is being pressed on it, okay? Liquids, which most of our body's made up of, can't be compressed, right? They can't be compressed. Um, and so that's sort of a bit of an irrelevant part of things. Although there is stuff to do with, um, if you go diving down under the ocean and you experience much higher pressures, and your scuba tanks that you take down there are allowing you to breathe by, regulating their pressure to the outside pressure. What ends up happening there is that under higher pressures, gases can get forced into solution. So if you imagine, say, like a bottle of Pepsi or Coke or something like that, you'll notice that when you open the cap and you release the pressure, right, the gases that were dissolved into the liquid are no longer forced to stay dissolved, and they come out like bubbles, right? Especially if you shake it up, they come out like crazy. So who's heard of the bends? Have you heard of the bends before? So the bends is if you go diving really deep, right? Because you're under a lot of pressure, the regulator in your scuba tank gives you much higher pressure air. If it did not, the weight of the water would crush your lungs down and you would not be able to inhale. So the regulator takes care of the difference in pressure, right? But because essentially your whole body's under pressure and all of your, respiratory system is now under higher pressure, more gas gets dissolved into your lungs. Well, that's not a problem. Although I guess if you get too much, you get nitrogen narcosis, but that's another story. But if you come up too fast, right, much like quickly opening the bottle of Pepsi, all of that gas can come out of your blood, and well, you could have a stroke. You get the bends, right? It's very painful. There's literally gas bubbles in your blood. So the cure is you've got to be put back under pressure to force that back into your blood, and then slowly over time they decrease the pressure back to atmospheric pressure and let that kind of dissipate, allow you to breathe it out. So the rule when you're diving is always to be exhaling and not to come up to the surface too fast. The other thing that can happen, if you remember, you have pressurized air in your lungs. So if you inhale and then you shoot to the surface, it's just like taking a balloon and taking it way up high where there's low atmospheric pressure, and your lungs can explode. When I went scuba diving, and they say always exhale as you come up, and it's really kind of neat. You take a breath at the bottom, you inhale at the bottom, and as you come up, you exhale. You can literally exhale for like the whole time you're coming up. Yeah, it's really quite interesting. Who's ever done that before? Anyone ever done that? Yeah. Well, if you ever get the chance, it's pretty neat. And take your gas laws with you. They train you in the gas laws during scuba. But if you do this first and you have a good understanding, part of the course is writing out how the gas laws work. If you understand all of this stuff, you'll ace that part, and it makes a lot of sense, right? It's not just do this because we said. It's like you get why you need to do that. Yeah. Okay. Right, 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 for sure. Okay, so that's the pressure part. Um, So let's talk about how does temperature play in here, okay? Because temperature also plays a role in pressure. Temperature and pressure are related. So if you imagine, right, you have your little container here, and remember that pressure is the collective collisions that are happening with the walls of the container. If we start to heat this container up, what are we going to do to the overall kinetic energy of the particles inside this container if we start to heat it up? So we're going to increase it, right? So in other words, the particles within here are going to start to move, on average, much faster. They're going to collide with the walls more often and with higher kinetic energy, and this will cause the temperature to drive up. Or sorry, the pressure to drive up. The pressure goes up as you increase the temperature. Goes up. Okay, so pressure goes up as temperature increases because these particles are whipping around much more quickly. So what is temperature? Let's go back to talking about temperature. We did before, but temperature is a measure of the mean, which means average, right? Mean means average, of the average kinetic energy of the particles in the gas. And there's a symbol for that. When you're talking about the average kinetic energy, it's EK with a bar on top, okay? So bar means average in this case. Now, I'm not sure how much time we have left. Not much. Okay. Yeah, we'll just leave it there because we're going to have to get into some formulas after this. So this is fine to stop here.